A warm welcome to today's webinar on the topic of selecting passivation techniques for CRA to complete fabrication. The webinar is organized by MISIF, the Malaysian Iron and Steel Industry Federation, and conducted by the International Molybdenum Association and the Nickel Institute. Today's presenter is Dr. Graham Sussex, Nickel Institute consultant. I'm your host, Jörg Schweitzer, Manager Market Development in Southeast Asia. With this, I would like to wish you all a very interesting webinar. Over to you, Graham.
Good morning. Yes, good morning. These three pictures are examples of what you, well, two of them, what you don't want to see on your nicely fabricated piece of stainless steel. On the left, we have quite reduced corrosion resistance underneath the fairly heavy heat tint there. And hopefully that was just taken as an intermediate picture and then it was treated. On the right, we can see what happened when a nice piece of stainless steel was taken on site and some careless person did some grinding on carbon steel or galvanized steel and splattered bits of steel, ordinary steel, and it corroded and rusted and looks a bit like a leopard. And in the middle, we can see the difference between an electropolished elbow in the middle and just abraded surfaces at the side, which don't have quite the same level of corrosion resistance. And we'll talk about that in a moment. Ah, damn it. What's going on? There we are. Okay, this is basically a description of what I just said. And you can look at it, it's there and it's included for completeness. So I just want to talk a few scene setters on welded stainless. So it's got a passive film on the surface. It's chromium oxide hydroxide. It's called passive. It's nanometers thick and it resists corrosion. Starts to repair immediately. That's within milliseconds after it gets damaged. What's in stainless steels? Well, chromium is the important thing. Molybdenum is another very important thing, and nitrogen also gives you a significant increase in corrosion resistance. But as far as the mechanical properties, physical properties, then it's the nitrogen and the nickel and the manganese that are going to actually affect that. And the numbers in terms of concentrations and so on are given down the bottom there. So how do you actually assess whether a particular stainless steel is going to be high or low corrosion resistance? You can do it by this pitting resistance equivalent number, which is really just a number based on composition. For ferritics, the N term is usually omitted because basically you don't get much nitrogen in a ferritic. If people talk about a super stainless steel, then it means that the pitting resistance equivalent is more than 40, and it basically will stand up to seawater. Nickel doesn't appear in that. It's very important in terms of composition, in terms of physical properties, but nickel does not affect the corrosion resistance for stainless steels. And it's only an approximation to compare grades. If you've got a difference of 1 or perhaps 2, it probably doesn't mean much in the way of difference in corrosion resistance, but for overall going up by 5 or 6 or more, it makes you get distinctly better corrosion resistance. Why are clean surfaces important for welding? Well, because you've got some molten metal there, it's going to freeze from the outside. All the defects in it are going to get pushed into the middle, and you wind up with a center line band, which could be susceptible to corrosion or to fracture. The other thing about welds is that the molten weld will lose some chromium, not a lot. It'll certainly lose nitrogen, and so the pitting resistance equivalent will drop. And if you're talking about the recommended fillers, typically they're going to have greater corrosion resistance than the bulk metal, so that the very small weld in the middle is going to be cathodic and not corrode, compared to the very large anodic piece of stainless steel that's around it. If you're talking about duplex, then you make sure that you've got more nickel in the actually filler metal, just to keep the microstructure right and make sure that you've got enough austenite to ferrite ratio. Okay, so I'm going to talk about, this is the topics I'm going through, and yeah, you'll get there, you'll see it. That's really just a summary. Okay, so what is cleaning? Taking off the surface debris so that you can get oxygen into the surface and keep the passive film going. It's not static, it's massively regrowing itself from damage. If it gets corroded a bit, then 1,000, 10,000 times faster. You clean off debris that might mean difficulty with welding or could cause stains when they get degraded by acid treatments, and typically that's organics. So typically it'll slowly, a pickling process will slowly etch the bulk of the stainless steel. It'll take away any carbon steel contamination just like that, whether it's rusty or not, dissolve out the heat tint and any underlying chromium depleted layer. I'll talk about that in a minute. If you've got manganese sulfide inclusions, it'll take them out, so you get a micro pit, but equally you don't have a point where corrosion is likely to start. And if you've abraded it, and you'll see pictures of this in a minute, then it'll take those flakes away. And then you wash the thing and you do it fairly thoroughly, particularly if you've got crevices around, you make sure it was a good wash, and you get a chemically passive surface about the same as a 2B cold rolled. The definition in ASTM A967, and I'm going to talk about ASTM quite a bit because it's what I'm familiar with particularly, formation of a nanometer thick oxide based, and there's the definition as used there. The chemical process, if you're using oxidizing acids or chelating chemicals, and I'll talk about what that actually means, and that will take up free iron and steel that are sitting on the surface, contamination, called contaminant iron on the new edition of A380, which will come out soon in inverted commas. It'll selectively remove iron from the surface layers, so you get a higher chromium to iron ratio and better corrosion resistance. Hey boy. And it'll get a thicker passive layer on the surface. Again, better corrosion resistance. The problem is, if you haven't cleaned oil and grease and things like that, organics off the surface, then you put the acid on and it very often gives you nasty black stains, plus also stuff floating on the surface, which coats everything when you pull it out. This is a picture from Outokumpu, I think, looking at the various things that sit on the surface and you've got to do things with it, and we'll talk about these on the way. But the spatter just shouldn't happen, of course. Organic contaminants, well, you get rid of them by various means on the way. So what actually limits corrosion resistance? Well, if you're talking about welding, the very first thing is just the fact that you heat it up and you get this, as you can see, these bands of rainbows on the side, which is just thicknesses of the oxides sitting on the surface, which is not protective. If you do experimental work and look at versus the colors there, what the corrosion resistance is, as measured by this pitting potential on the left, then you can see that very rapidly your lovely 316 becomes not much better than 304, and eventually they both wind up being about the same as a 12 chrome, or perhaps even a bit less. So if you've got heat tint, you've got lots less corrosion resistance, and if you've got really bad heat tint, then you may as well be using carbon steel. This is from an AWS standard, American Welding Society standard. It's been used for food industry here, and they basically put some oxygen with, or a bit of oxygen in a gas going through, and then did a band around the outside and said, okay, what's acceptable? And they decided that for food industry stuff, about 3 was about there, so the one with the nice tick on it. And that corresponds to somewhere between 40 and 50 parts per million of oxygen, compared to the 20% in an atmosphere. So that's fine, but it does work also, quite apart from the food business, with corrosion initiation generally, and that was work done by Sandvik and a lot of other people. So it's a generally accepted thing. So what happens when you actually do a weld? Well, you put the stainless steel weld metal in, but you heat everything up, so you get this oxide film forming on the surface, and on the underside, unless you've done something really clever like purging it, then you get the heat tint as well. You get in that region, pointing out there, the little wedge-shaped bit, that's where it stays hottest for longest, and so the chromium will diffuse more rapidly up, and so in that area you get a lower chromium level and therefore lower corrosion resistance, quite apart from the heat scale on the top. And you've got to take it off. You've got to get rid of it. And if you're just sort of lightly etching the thing, you're not actually seriously working at it, you're probably not going to do it. You may find that fatigue strength is going to be reduced by the microstructure of the weld. This is not the sort of thing that we're talking about with carbon steels, where you get actually heat treated and rapidly quenching itself, and you wind up with hard spots, basically, which you have to measure. Here, we're just simply talking about an area where you've got a bit of distinctly less corrosion resistance. And people also worry about what happens in terms of strength if you've got a piece of cold rolled stainless steel. Well, in fact, it's only the very, very bit right next door to the fusion line which could be affected. And if you look at how long you have to have something hot to get reasonable annealing, then unless you're an enormously thick piece of metal, it's just not going to happen. You do have to worry about how big your fillet weld, for instance, is, because if you look on the lower diagram, 3.5 mil thick, the 7mm fillet only needed to be 4 millimeters thick, but because it's 7 millimeters thick, you wind up with an enormous bit underneath where you've actually got quite bad heat tint, and you've got to do something about it. This is a case where somebody has welded a piece of pipe onto a large diameter pipe, and they didn't bother cleaning it up afterwards. And so after they'd put and in fact it was salt water because they're talking about a desal plant, you wind up with corrosion in that area. This is the outside of a piece of pipe, and somebody has ground the thing to take the heat tint away. But as you can see, they're looking at an austenitic, well, you don't know, but I'm telling you it's an austenitic stainless steel, and they've overheated it because it's not good in heat conduction, and so you get that bluing. And that bluing is the same as the heat tint effect. You've got the reduced chromium layer level underneath, and so that has to be taken off if you want to get good corrosion resistance. We'll come in a moment to the bit about surface roughness. Here's the other problem. I showed you the overspray of carbon steel on the right side of the first slide, but here on the left, we've got a lovely case where somebody said, oh, gee, we put this lovely polished piece in, and we've got a little bit of something there. We'll just give it a quick touch with the brush. And unfortunately, the last time it had been used, it was on carbon steel. And so you've got carbon steel put back on, and it's a mess. Here we've got a whole series of channels, and I was out on site and it had been raining, and looked over there and saw this bundle of lovely bits of angle that had been cut out, but unfortunately they've contaminated from the actual guillotine on the edges, little bits of carbon steel from having cut something and contaminated the blade. And maybe it was just something that had been left dust. They had a mixed metal area of workshop. I'm not sure. It can be fixed, just pickle it, but really it shouldn't have happened. And keep going. Oh, sorry, one little point there. Down the bottom, don't go abrading it, because if you start abrading to take off carbon steel, then you're basically going to smear it out. And roughness. Here we've got several levels of roughness going from 120 to 240 to 400 grit. And on the 120 grit, you can see all sorts of little bits on the surface where the grit is a bit too big to be strong enough, and it starts tearing metal rather than polishing it out. The 240 isn't so bad, and by the time you get up to 400 grit, yeah, it's pretty good. The number, the surface roughness there, RA, there is a standard, a European standard, which says 2K of no more than 0.5 micrometer RA, and that's it, EN 10088.2 for the sheet. The other thing that can happen is if you're out in the open and you're in a salty atmosphere and you've got deep grooves, then it's quite likely that when those grooves get filled up with a bit of salt water and it dries out, then you're going to get a very, very concentrated solution for longer, as shown on the bit on the right as it dries out under the sun. Lovely diagram, not from me, unfortunately. I didn't think of it, but it was done by a fabricator in Brisbane. So what happens if you try and test one of these things? Well, down the bottom, we've got the RA greater than 1 micrometer, and on the right, we've got RA of 0.3. Put into a salt change, salt spray test. Terrible test for stainless steel, not very realistic, can't be converted into hours of salt spray equals months of, because you've just got continuous wet salt. But you can see that the rough ones, a lot worse corrosion resistance. And typically RAs for 2B can go from 0.1 to about 0.4. BA can go from about, that's bright annealed, 0.06 to about 0.1. So you'd expect bright annealed to be better corrosion resistance. And a mirror polish, it's a lot of hard work, but about 0.02. And interestingly, the roughness is going to be less important if the metal is pickled. Why? Because if you look at those two pictures at the bottom, or the pictures previously, you can see that if you pickle something, you're going to take all these little flakes of metal away, and so you don't have micro crevices. Next thing, all steels have manganese in them, and most of them have some sulfur in them. Depends how much sulfur. But here we've got 304, 317, which is a bit up on 316, and the 6% moly grades. So they are very corrosion resistant. And they're done with a test. We're actually looking to see if we get any corrosion from these sulfide inclusions. And the picture on the left there is highly magnified. That's about a micrometer across where there used to be a manganese sulfide inclusion, but it's been cleaned up and taken away by actually just giving it a pickle. So up the top, less than 003, and often if you're talking about sheet, it'll be 000, and you really don't get much in the way of it. Whereas if you look down the bottom of your piece of bar, greater than 0.015, and it will be quite often a bit closer to 0.03, which is the limit, and you get these spots, manganese sulfide. 304, it's worse. 317, it's not quite as bad. And the 254, or the 6% moly grade, yes, it's still there, but it's quite hard to see. And the other thing that can happen, if you've been cleaning up your surface with abrasive blasting, then you may well break it up and put all sorts of rubbish into the surface. You might do abrasive blasting to paint it if you wanted to, or to match appearance. You've got a bit of bar or a bit of sheet, or you're trying to match up a number 4 finish on welds. But that bit is usually done by glass bead, so you really don't take much metal off. But if you start getting serious and you're using silicon carbide or aluminium oxide or one of the engineered zirconia types, then you can get different colors. And that's basically because you're trapping little bits in. And it shows up. You've got lots of mini crevices around those particles. If you actually pickle the thing and look in the bath in the bottom, you see all sorts of bits of the abrasive, broken off abrasive left in the bottom. So, well, people clean carbon steel by wire brushing. So why not use stainless steel wire brushing? Well, unfortunately, it doesn't work terribly well because stainless steel wire brushes aren't all that vigorous. And it will remove surface debris from a weld if it's still warm. Won't take heat tint off. You basically just burnish the thing and make it look bright and beautiful, but doesn't really improve the corrosion resistance. And because it doesn't take off much in the way of metal, it certainly doesn't deal with the chromium depleted layer. Certainly it won't deal with it right next door to the weld, and even further away from the weld, it won't do an awful lot of difference. I should just make a note there. Quite common to use automated strip polishing around tank welds. And yes, that's good because you basically get a nice smooth surface. You don't have the weld mound there, which can trap stuff, and you get a good uniform polish. But then usually, if you're looking for corrosion resistance, you'll have to do a chemical passivation of some sort. Not pickling, just passivation. So what sort of cleaning processes can you do? Now, if you get hold of the ASTM A380 2017 version, section 6.2 in the new version, if it comes out this year, it's currently being debated. It'll be 7.2, but 6.2, and it goes on for a long way. So you degrease with detergents, pressure wash if you have to, quite often hot alkali if you're trying to get rid of grease, and then thoroughly rinse it. And make sure there's nothing left of your cleaning agents. Very effective for anything organic, unlike the acids which tend to crack them. If you're using solvents, do it with agitation. It's a lot better than wiping, and it also seems to be better than prolonged soaking. And that's probably because if you've got crevices around, and I'm not just talking about fabrication crevices, I'm talking about the sort of crevices you can get around a piece of rough surfaces. But anyway, and the other little point that's into this, if you're using chlorinated solvents, then you've got to be very careful to make sure you get rid of them, because if the thing's going to be heated up, then it can degrade and you wind up with hydrochloric acid. Once you've taken those things off the surface, then often the formulation will have some dispersants in it, which actually holds the particles of soil or whatever it is, and I don't mean dirt soil, I mean rubbish soil, in suspension, and stop it from sludging down if the flow rates get a bit low. And at the end of all that, you have a lovely clean surface. And you say, oh, right, well, we'll just stick that in the workshop, or we'll put it where everything can go on it, or maybe where people can walk on it, and it's perishable. You also need to be careful that if you've got intermediate dry stages between doing one step with, say, detergent, or one step with solvents and then to detergents, you really don't want it to dry out because you can get stains. That also can happen if you're doing the pickling to passivation steps. We'll come to that in a moment. So it's perishable, so keep it clean, be careful about handling it, and make sure you don't resoil it. The 380-217, all of there's 12 parts in it. You would have to take out any sensitive items. If we're talking about an installed system here, it's got all the instrumentation and stuff. You may have to supplement the flow in areas where it's going to be low. So if you've got a large diameter pipe and you're running small diameters off it, they're good, they're nice flow, but the large diameters, particularly if you've got spots where it's actually lower point, you need to make sure that you can completely drain it. And if you're looking at really sensitive systems, then maybe it's coming in having been pre-cleaned somewhere else, and then you've got to make sure that you don't recontaminate it by adding on anything else. And sometimes you actually flush with the process fluid. But much more typically, if you don't have heat tint in, then flush out any debris, degrease it, and quite often warm sodium hydroxide. Sodium tends to be the salts that get used. And you might have surfactants, basically, things that will lift stuff off the surface. Take any ion contamination off. This is in order for steps. There shouldn't at this stage be any ion contamination, but you don't actually need to have anything heroic. Phosphoric will do it, although it'll do it a bit more slowly than a dilute nitric solution. And then you can repassivate it with dilute nitric, so that would be combining those two steps, or chelating agents, and I'll talk about them, or peroxides. Peroxide basically is lots of oxygen. The other way of doing it, of course, is to use a pure oxygen atmosphere over it, but you don't want to do that too often because A, it's expensive, and secondly, it's a major fire hazard. So if you've got heat tint, then you're going to have to pickle things. And now I'm going to go through pickling and passivation and a couple of other bits. And yes, high temperature rolling mills, they do tend to use hot hydrochloric, but for a very short time because they want it to be really fast. It's going to give them pitting, but that's on hot rolled material. Normally, if you're talking about pickling after fabrication, you use nitric hydrofluoric. The hydrofluoric does the hard work and the passivation sort of tempers it a bit. There is actually sulfuric acid treatment in A380, but it's followed immediately by a nitric hydrofluoric treatment. Low levels of hydrofluoric give you slow pickling. High levels give you fast pickling. Greater than 3 or 4%, yes, it's quite a bit faster. But I have seen places where you had to go up about 9% or so. Some idiot had done some welding of thick pipe, and after the second pass, they turned off the purging gas, and so inside it was as black as the night. Time and concentration, if you look at A380 for recommendations, you won't get them. What you'll get is a bundle of suggestions, And you can see here's a couple of suggestions, and they're sort of barn door. They run all over the place. So it's a matter of working out how bad the heat tint is, and the people who do it routinely will know what length of time they need to put on. So how do you do it? Well, you can have thixotropic pastes and put it on. That'd be typically a small sort of job, or spray pickling. And I'll show you a picture of that. And the person there is wearing careful protective gear, and you'll see the picture too. Or you can put it into a pickling bath. And if you're putting into a pickling bath, then typically it's better to stir it a bit. But note that the effect of stirring is less apparent as you get to higher and higher corrosion resistance, because as you go down that list there, you go to higher corrosion resistance, going from 304 up to the super austenitic stainless steel. Oh, one thing about pastes, you put them on and you will exhaust the acid. If you leave them, then it'll dry out and you'll wind up with stains. And I had a classic case. I was on site for something else, and some people came in to do some pickling of a whole lot of welds, and they went right along this line, 300-400 meters, pickling everything, and they went off to lunch. And when they came back, it had dried, so they had to start again. Expensive. The rainbow effect, it's just simply like a oil slick soap bubble. You're getting reflection from the top and the bottom of the heat tint, and as it gets thicker, it gets blacker. And on the right is what it should look like after you pickle it. This is the man wearing, I think it is a man, good protective equipment. Stir the spray up so that it just doesn't settle, and apply nice and evenly. And because you're putting wet on wet, you need to be very careful to make sure that you don't miss bits and don't let it dry out. So the other thing you need to do is make sure that you've not depleted your pickling acid. I mean, you don't use fresh acid every time. Well, you might, you will if you're using paste. But if you're using liquids, then watch out for how much builds up. A380 says if you're pickling, check the iron content. If it's up to 5%, replenish the whole thing. If you're passivating, so you're not trying to pickle things off, then 2% is the limit. This is a case of a thin piece of well, it's a relatively thin piece of a tank. And you can see there are two welds, a circumferential weld and a seam weld on this outside of this cylinder, and it was put into fairly warm acid, and it was old acid, so there was a lot of iron in it. And the ring around there is where it's gone right through, because you've got a sensitization. That area is much more susceptible to corrosion, and so you've got perforation, and the thing had to be thrown away. They basically should have made sure that their acid was okay. That leads into what happens with sensitized or hardened nitride or carburized. They'll get into granular attack unless you do things with them. And you can. Basically, you do an alkaline treatment on the way. The free machining, they'll pit unless you use the alkaline treatments for manganese sulfide inclusions. And it's a recognized technique. If you've got crevices and your hydrofluoric acid is retained, then unless you very carefully rinse the thing, you might even actually do some neutralization, then you'll get later weeping and corrosion. If you talk about martensitics, then you're pickling them, you're potentially generating hydrogen, and so therefore you would normally bake them at about 150, so that's not going to heat treat at all, but it will take the hydrogen out. It's something that they do routinely in electroplating of stainless steel fasteners, but this is, pardon me, if you're talking about martensitic stainlesses that have been pickled, that's a precaution. And if the pickling solution dries out, as I've already said, uneven, and you have to go again. Here we're dipping, there we're putting on paste, and note the protective equipment. Here we've got rinse baths, so starting from the far end, it'll be washed, then it'll be pickled, washed, degreased, pickled, rinsed, passivated, pastivated, and then washed again. So it's a bit of a process, but it can be automated. And here we're spraying, and it's red because it's a Vesta red, and it's basically spraying this stuff on. Interesting exercise that, because the color tells you where you've sprayed. So it's, I won't say foolproof, but it's certainly pretty good. Okay, so then afterwards you rinse it, high pressure rinse to get the last of the stuff off, low pressure wash first to get most of it off, but the high pressure to get stuff out of crevices. It's wet on wet, so you've got to be very careful about that. And you may get smut on the surface. I'll show you a picture in a moment. And then dichromatic treatments work quite well. Ultrasonic stirring, people say, oh, yes, yes, but you don't really need it. Just enough. You don't need to go swirling around fast. You just need to keep things moving. And you certainly don't need to use demineralized water. You certainly don't want really lousy water, but sort of potable water is quite enough. And this is smutting. Basically, it wasn't rinsed properly, and it's just deposited on the surface. You might use it with a dichromatic treatment, and that works fairly well. So what does the surface look like after it's been pickled? Well, the top one is you've got some areas that are clean and some not. Here is about where it should be, nice smooth surface. That's grain boundaries. You can see those black lines around, and that's micrometer level. And if you overpickle it, then the thing goes really nasty and grey. And that's because you've lifted off the top surface and you've got a moderately uneven surface, which basically traps lots of light when it reflects off. But it also will trap muck and rubbish, so it's not good. Okay, so pickling, that's taking off stuff from the surface. Those three standards, 380, but 967 is specifically about passivation, and the American military standard 2700 or QQ35, I think it was originally, is the thing that was prompted the development of 967, because the military wanted to be able to give their contractors something that wasn't military as a standard. And probably quite importantly, 967 says in black and white that while passivation will occur with air exposure of clean surfaces, chemical treatments may be used to augment and improve the passivation surface process. So nitric acid, nice oxidizing acid, high levels of oxygen or hydrogen peroxide, and that's used by a very major company. But the trouble is oxygen, hydrogen peroxide will not dissolve scale, and it won't take away metal flakes and so on, whereas nitric will. Phosphoric or sulfamic acid will clean away steel smears. It'll get rid of corrosion product or some scales, but it won't oxidize it. It won't chelate the surface. It won't selectively take out iron. So it won't improve the passivation of anything other than contaminant iron. And the chelating treatments, citric acid, oxalic acid, EDTA, they all will improve the passive film. They will increase the chromium to iron ratio and give you a better surface. This is out of ACOM number 4 in 2006, and it's looking at the pale colour is immediately after they've been passivated in those various things, and then after 3 days exposure to a mildly aggressive environment. And you can see that this finish one with hydrogen peroxide actually did very well. And hey, guess who actually sells the stuff? But it's quite true. Whereas if you're talking sulfuric acid, dilute sulfuric acid, mind you, and very dilute, and just straight air passivation. So the difference between the one on the right and the one in the middle is simply the amount of oxygen to form the oxide film on the surface. Citric is a chelating agent, and nitric is just straight oxidizing agent. Here's some work done in New Zealand, published in Corrosion Science some years ago now. 25% nitric for immersion for about an hour, and then they measured the corrosion resistance by looking at the chromium to iron ratio on the surface, and it's up to about 2 in the middle at about 20–30%, and then across to the edge just measuring pitting potential, and again at about the same point. If you move right up to 60–70% nitric, then it tends not to be so good, because it taking away carbon steel, simply because it tends to passivate the surface of the carbon steel. You've got to be very, very concentrated for that to be a problem. and basically the stuff that's around for passivating paste tends to be around in the 20 to 30%, which is about where you want to be if you look in here on both scales. And that's what I just said. This is a picture, and you can believe the 10 nanometers scale up the top, and you can say, hey, come on, it's a fake. This is actually a bit of ferritic stainless steel, not austenitic. But you measure the thing. This is a picture, but you can measure it by hitting the thing with a beam of neon, bounce the metal off, and just measure it through a mass spectrometer. So why do you use dichromate with passivation? Nitric plus dichromate is quite common. It is an inhibitor, and it will stop the attack around the sulfide inclusions if you're talking at free machining. And it will also deal with the area around carbide or nitride precipitates. If you've got, in carbide case, it's sensitized, in nitride case, it's hardened, but it will actually enable you to do the treatment and get a passive film. A380 has got dichromate nitric solutions for bright and polished finishes. So it looks very bright and shiny. You do not want to etch the surface. And so you put some dichromate in basically to give you high corrosion resistance, but as in high iron to chromium to iron ratio on the surface, but without changing the actual surface profile. 967's got one of the dichromate nitric in it, and then has a detailed list of what you can use, different concentrations. A lot of that came from AMS 2700, because there's 5 out of their 8 treatments have dichromate nitric, and one of them has even got a bit of electropolishing in, a slight potential put onto it, but that's not used very often. But 2700 is used a lot, and 967 is used a lot for people who want very high corrosion resistance. And 967 basically grew out of AMS 2700/QQ35, the 2 military standards. So what does chelants do? Hey, look, the stuff that the dentist puts on your enamel in your teeth is a chelant. It takes a bit of calcium out, gives you a slightly rough surface so they can then glue the whatever it is they're gluing into your teeth. But this is perhaps a little less benign. They've got these claws. They've got charge. COOH is a large part of it, and that traps, because there's negative ions there, it will trap the positive ions that are on the surface. The as I was saying, carboxylic acid group is the basis, but the pH and the temperature have got to be correct for the metal to dissolve and to be ionic. And it's quite important, because once it's picked it up, then it's heavier, in inverted commas, to actually take it away. Otherwise, you'll tend to get sludging. And other chelants. This is EDTA, that complicated one, and you can see there's lots of negative charges on the oxygen atoms, and it's trapped the iron right in the middle, and that's a little standard model. Citric acid, there's 3 hooks there, so they actually can take quite a lot. There's 3 of those OH danglings, and that's polar, so it traps the positive metal ions. But you've got to get them into solution. Just means the pH has got to be right. And I've already said this bit about heavier. So just as a summary of that, you clean to get the surface to actually show the metal there. So take off the soil, and I don't mean dirt, I mean just general grime, grease, oil, etc. And water and oxygen will grow the passive film. If you've got something that won't come off, like heat tint, then you have to do a pickling process. And that is controlled attack of the stainless steel. It's got to be, because in the chrome depleted layer, you've got some corrosion resistance, just not enough. It'll take out an embedded iron just like that, take out the manganese sulfide inclusions, and will slightly dull the surface. And if you look at places where people put pickling paste on and left it for a while, then you do get this dulling of the surface. And once you rinse it, hey, you've got a passive film. If that's all you need, that's all you need to do. You can walk away from it. And as from hopefully the next version of 380, the title of it will actually say that it pickles and then passivates. So up until now, it was just talking about passivation. Slow changes. And then you go for passivation. Clean, moist air, that's the definition in the 967, will passivate it. You won't change the appearance of the surface, but it will get better chemical passivation if you do chemical passivation. But air passivation is usually going to be okay. So in summary, all those things are going to affect passivity. Cleaning won't affect stainless steel metal. Pickling will etch the stainless steel and will passivate. If you need better passivation, then yes, you can do it. You increase the chromium to iron ratio on the surface, but it doesn't dissolve the actual metal structure. Lots of ways of doing it. Oxidizers will passivate. I've already said that up the top. And the chelating hooks will remove contaminants and the less resistant elements like iron. Okay, so let's talk about other passivating things. One of them is electropolishing. Here you're not using chemicals, here you're using electric current. You might take a few tenths of a micrometer off, but not much, but you will round sharp edges, and I'll show you why in a sec. It makes it easier to clean. And that's why it's used often, well, it's always used in pharmaceutical, but it's often used in food as well. Selectively removing the lower corrosion resistance materials. And so I've put it there rather tongue in cheek. It's the ultimate stray current. Take off conductive oxides. Now, unfortunately, the oxides that form when you weld stainless steel are usually ceramic-like, so they're not terribly conductive. And so you're taking it away by undermining at the edges or from the defects, and there are lots of them. Now, this is showing you why you get a smoother surface, because electrostatics says that if a current flows from a surface, it will flow from peaks, from sharp points. So where you've got lots and lots of crosses over there, there's lots of current flowing, and down the bottom of the dips, there's very little current flowing. So if you did a cross-section of this and actually watched it, you'd see that the peaks gradually shrink into the surface. What does that mean? Well, imagine a beam of light coming down and hitting the side of one of these slopes, bounces off, hits the next one, and stops. And so it's dull. So take things down to gradual undulations, and it strikes there, misses the next one, and comes back. So you get a really massive increase in the reflectivity and a real deepness, a luster of the surface. Typically, roughness is going to be decreased by 20–25% maybe, but we're talking at the fractions of a micrometer level. We're not talking about millimeters of loss. Okay, your stainless steels are normally polished. This is the grain structure, and this outer layer on there, the bilby layer, is sort of cold work. If you actually do some polishing on the surface and you use various grits, then you're going to get that sort of roughish layer there, and that will depends very much on what you're actually doing it. If you're looking with aluminium oxide grit 150 or carbide, and as you can see, as you get smaller and smaller in your grit size, the depth of the disturbed layer, this bilby layer, gets less and less. If you electropolish it, then you've got a relatively softer surface, which in theory might actually affect the fatigue resistance, but in practice, it's usually not an issue. Okay, here's some electropolished stainless steel. There's the Tamarana beach in the background, and the only difference between these two is 4 years of exposure. We've got some crevice corrosion around the where the washers are, and we've got one case, perhaps two cases, where the nut is, or the bolt is actually not stainless, 316 stainless. But by and large, the electropolished stainless steel, it's pretty rough. It's about 1.3 micrometer RA. It's just very much corrosion resistance. And if you think that's been washed down, you're dreaming. It's the back of a life-saving place. Nobody goes around there. And people say, well, okay, yes, we can electropolish, and sure, on the right there, we've got bits down in Brisbane River front. lovely polished up and then electropolished. So it's just sitting there looking lovely, and people run their hands along the top and they don't go, oh, something a bit rough there. It's just good. Up the top, we've got two 2205 pieces of elbow. And the one on the left has been electropolished and the one on the right hasn't. So you don't get the really bright surface finish, but you do get a massive improvement in the corrosion resistance and some improvement in the brightness. Why? Because you've got both ferrite and austenite in the duplex, and so it doesn't go the same way. And how thick is the oxide layer? Well, here is a thing where you throw a beam of neon, I think it was, on the surface, and whatever comes off the surface in ultra-high vacuum, run it through a mass spectrometer and say, well, is it oxygen, is it chromium, is it carbon, is it nickel? And basically where the oxygen peak stops in terms of depth, that's about the thickness of the oxide layer. And it's also about the point at which the iron comes back up. So if you look at the iron levels there, or the iron counts, then they've dropped right down in the surface and the chromium is distinctly higher. So you're looking at more chromium than iron in the surface. And the nickel doesn't change all that much. What are the limitations? Well, reasonably uniform, and I've shown you the bit about the duplex stainless steel, and you don't get really bright things, but it's a bit worse if you're, say, bending a table leg or something, and you're then electropolishing it, then you may well find up that in that area you get an orange peel effect. It just means that you don't want to have too much cold work. Ferrite to austenite ratio, not a major difference because of what I've just shown before. You've got to pre-clean to make sure the grease goes off, because grease is an insulator, anything that's non-conductive. And again, don't go drying it out, don't pull it out and leave it around for a bit and say, oh no, we've got to do a bit more. Same very much as with pickling and passivation. And then you clean off the electropolishing chemicals. That's easy, of course, you just wash it. You actually usually need to put a bit of acid onto it to clean it, because the mix for the electropolishing chemicals includes some stuff to actually make a surface layer, which gives you some more uniformity. Don't bother about the chemistry of it. It's just you buy the stuff and you use it. And then you have to treat the waste solution, because, hey, all of these things, you've been treating stuff which has got lots of chromium, lots of iron, so you've got heavy metals. And so you've got to get something down to the levels that the EPA is happy with. So what's the difference between a mirror polish and electropolish? Mirror polish, you've done it mechanically, so you get a very sharp image. It's flat to the limit of what your past particles were. Very good corrosion resistance, but you haven't done anything about any manganese sulfide inclusions and so on. So probably you need to do a passivation process just to take them out. And that might be a citric or it might be a nitric. But you'll get very bright and sharp reflections. Electropolishing, well, you can generate gas bubbles, or the surface might be a bit rough. You're going to smooth it a bit. You're going to take the sharp edges away, but you will not get the really bright and sharp image. And the roughness, well, depends on what you started with. And you will get really excellent corrosion resistance, but it's going to depend on how cleanable it is, which depends. If you've got a wavy surface over a few micrometers, then you're not going to take it all off by the electropolishing, but you will get this luster for the reasons that I talked about before. There are electrical cleaning things. The first ones, you dribbled some electrolyte down onto the surface, you put a current between it, and you basically did an on-site thing. It was slow. The sponge was wet, it got hot, and it didn't work too well. Then people cooled the sponge. That worked fairly well. And both of these, the one on the left is just a straight stripe along across a weld, and you can see the change. And the one on the right is looking at a more complicated arrangement. And yeah, the surface will get brighter. The smart people decided they'd work on it, and the people who originally took out the patent on the TIG brush let it lapse, for heaven's sake, but still. And this is one of those things. Carbon fibre brush, so it's conducting. You use a relatively in a benign acid, usually based around phosphoric, with some other chemicals, and it brightens it up. You're putting current through a liquid which is resistive, and so it gets hot. It gets hot enough to spit. So you need to be careful about getting splattered with the acid. It's not really nasty acid, but it's pretty hot. So don't get it on yourself. And this is looking at potential as a measure of corrosion resistance across, and there's a weld on this side, imagine, and we're looking out here, nothing's happened, out on the left, and the full black line is the potential, and you can see very low corrosion resistance right across the thing. The original 2B is at 400, and the next up, the polished line, buffed up, yes, it comes up a bit, but it still dips right down in the area just near the weld where you've got low chromium, because you've got the chromium depleted layer. And then the dark dashed line is basically pickle paste. Yep, that comes down to about there and gets up. Oh, incidentally, the weld that was put onto this surface on the right actually had higher alloys, so the potential is going to be higher, full stop. The grey dashed line is looking at electrocleaning with AC plus DC, so high current, but not all the one way. And right up the top is electrocleaning with DC only, and so you get very good passivation. Now, you can also get very good passivation if you do a pickle followed by a passivate, but yep, anybody who says that you can't get it with a TIG brush is probably talking about something that's being done by the apprentice who didn't know what they should be doing. So, quick comparison. Pickling paste and electrocleaning can give you better corrosion resistance, mild acid in the electrochemical cleaning instead of the nitric hydrofluoric, which is nasty stuff. They're both going to be manually applied, and if you're talking about putting pickling paste on and you take it off too soon, then you haven't done the job. If you do the electrochemical cleaning and you don't run slow enough, then it may not be quite good enough. The electric cleaning rate is independent of temperature because it's the electrons that are doing the work, not the temperature of the thing. And look, double the corrosion rate or double the chemical reaction rate per 10 degrees C, that's chemical, but if you're using electrons, they just keep flowing. If you're talking about trying to electroclean something that's got really heavy heat tint, it doesn't work all that well because it's not all that conductive. And basically the wand stuff is very operator dependent. If people go jabbing at it, you're going to get sparks. If they wipe it too hard, they're going to wear the brush out. And if they don't keep going, then they may not take out the chrome depleted layer. I've seen recently automated kits that run along, but then it's a matter of setting it up to run at the given rate. But it will take off iron. It will also take off, contaminant iron, and it will also take off quite decent heat tint. Okay, so let's just talk briefly about lasers. And lasers are, I was going to say some very, okay, they're the thing that people say is absolutely great. Basically, the continuous lasers, yep, for drilling holes, cutting and welding, no problem, really good. Pulsed lasers, the way they're set up, they do a physical scan, but the pulsing is actually in the power that goes in. Very short heating cycles, you heat up what's sitting on the surface, and then it doesn't degrade the lower layers. Surface deposits get very hot very fast and break away, but the surface isn't melted. Now, it's scanning, lots of noise, and just think about it. Anything that's sitting on the surface is going to go into the air, so you get lots of microparticles coming away. The pulse durations go from nanoseconds, nanoseconds, picoseconds, and femtoseconds. That's going to give you quite different results for the energy density. The nano, obviously, you're putting more energy in, but and people tend to work at that. But some of the delicate stuff, people go up into the pico or femto. If you're doing continuous lasers, you can mark, you can cut, and whereas if you're just doing ablating, then you're going to use a pulsed laser down the bottom there. This is swiped from YouTube, as one does. The bright light there is this laser is scanning across in the dark blue direction. It's going backwards and forwards along those red lines. And why is it bright? It's not because everything is heating up a lot. It's because the particles that have come off are scattering the laser light that's coming through, and it's getting quite hot. So lots and lots of minor particles there. So what do? You put some local extraction on, and you come across that bottom bit there. You're scanning towards where the extraction is, and you take it away. It's just like weld fume, which you really shouldn't be breathing either. So people who do this sort of laser scanning system, unless they've got local extraction, they're, I was going to say asking for trouble, but certainly worry about inhaling or inspiring lots of dust. Okay, this is a picture. It's 3 bits of a picture actually, and there's a weld straight up the middle, and there's heat tint on the left and on the right. And the little bits are expanded up images, and you can see straight in the middle, straight down the thing, you can see the horseshoes of the weld as you're going. On the left, we've got a level of abrasion, and on the right, we've got a different level of abrasion, and you can see from looking in the background just how much of the heat tint is left. Now, that to me says that you've got quite a reasonable removal of the visible heat tint. I have absolutely no idea how good the actual corrosion resistance of that is, because people are remarkably reluctant to talk about it. And most of the stuff you look at talks about cleaning up carbon steel or taking paint off or taking concrete dust off. And there's equipment around, lots of people sell it. But whether it's actually, certainly it won't get rid of the chromium depleted layer, just doesn't. The metal surface doesn't get hot enough. If you get the metal surface hot enough, then you're likely to have been melting the surface as well, and that gives you a whole new problem. Heating cycle, it's just too short, too short. This is some titanium, and looking at blades, and the little box there is what the surface looks like after you've actually done it. So on the left there, it's the laser scanned area. On the right, it's the surface with the oxides on it. And it's titanium, remember, not stainless steel. And down here, we've got the laser cleaned area, a different sort of magnification, about 5 times greater. And on the right, we've got the as received, which looks blooming awful. And I think the dots are related to the way the thing is actually scanning. So it's promising, very high energy density, flash cooled by the bulk, and then breaking the surface away. Has been used to take paint off. Yeah, okay. That picture up the top, the first one I showed, was taking welds off a bit of carbon steel. But if you're not doing damage to a substrate, then basically any low chromium zones beside the weld, not going to change. Quite a bit of noise, pulsed, and I've said all of that. Yes, the nanosecond pulses rather than the femto get more energy into it. And weld tint fume. You could do sputtering tests. I don't know that anybody has. I'm surprised people haven't actually, because it's pretty straightforward. All you need is an Auger spectrometer and put one of those samples in, but that's going to cost somebody a couple of $1,000 and they don't want to do it. Okay, so chemical treatment summary, we're getting there. Pickling acids will remove the heat tint, take off flakes, and if flakes left from abrasion. And if you've got carbon steel slivers or heavy other iron contamination, then pickling acids will take it off. You've got OH&S from the hydrofluoric, passivation with the nitric or chelating acids. That's not going to remove. Number 3 isn't going to remove heat tint. The electrical techniques, either by the bath or brushes. Wet sponges, I wouldn't bother. They're slow for a start. And the electrical techniques are going to be independent of ambient temperature. And the lasers are an interesting thing, but people have got to do some work on it. And certainly, I don't see how it could take out the chrome depleted layer. Okay, so let's do some testing. there are a whole bundle of tests. There's the humidity, the misting, wet and dry, the copper sulfate, and the ferroxyl. And people who say, oh, ferroxyl's the best test, we'll use that. It's a pain to use. It really is. And it's ultra, ultra sensitive. There are electrical techniques, hysteresis things, but there aren't standards for it that are useful outside the laboratory. Surface roughness is not really, well, surface roughness actually is relevant if you're talking about something being clean. And certainly the pharmaceutical people have lots and lots of bits about surface roughness. But the food industry basically says 0.8 micrometer RA is okay. Auger spectroscopy, I'll show you what that means in a second. Oh no, I've shown it already, the bit about the depth of the oxygen going through. And that sort of test can actually prove that the process you're working works, because you look and see how thick the oxide layer is. If you're doing an inspection, gross indications for free iron on folds, edges, basically wet and dry it with an atomizer. I wrote a bit of a suggestion for this, and there was some wordsmithing done, and wow. Yeah, the 2017 version has got this thing saying, okay, put it on, make sure the droplets don't coalesce, run at least 8 or 9 cycles, 45 minutes dry between each, because as the thing dries out, it concentrates, and so most of the corrosion happens, if it's going to happen, will happen in the last little bit, in the last 20% of the time. It's quite a neat technique. Humidity cabinet, well, you don't normally have humidity cabinets for putting something big in. And chemical tests are so much more sensitive, but you've got to remove it if you're in food service. The sulfuric acid acidified copper sulfate, there's a different test if you're looking at a martensitic, things with less than 16%. And pink means there's free iron. The ferroxyl test, you will not get cyanide fumes unless you actually burn the stuff, but you will also pick up surface oxides, but it's a lesser colour. That if there's iron there, you get this really brilliant blue, whereas it's a bit late, a bit lower, sort of duller. And yeah. And I keep saying this, it's a spot test to prove a method. It's not a general inspection test. I've seen so many standards that say a complete ferroxyl test will be done, and it's a waste of time and quite expensive. Can do potential measurements. Yep. At a particular potential, the stainless steel will be corrosion-free. You can do it. Put it into a solution, look at what happens between 4 and 24 hours later after it's been damaged, and you'll see that it's actually come together. So this 4 to 24 hours, it's basically an indication of how well the passive film reforms. But you can use digital melting methods. You can do laboratory measurements. There are standards in this, but you don't go using it in the field. There was a technique put together where you could connect up, I actually demonstrated it in corrosion conference thing. And as soon as you abrade the surface, the potential drops way down, and as it reforms, and within the length of the torque, it came back to fairly close to what it had been before. You can measure millivolt meters, microvolt fluctuations. It's expensive, and yes, there are instruments that use it, but it's not widely used. The standards, A380, A967, they're currently being revised. If you're talking about electropolishing, those two standards are 192 and 15730 ISO. I think the same people wrote them because they're very, very similar. And this AMS 2700G, it's got citric and nitric passivation treatments. It's basically the more complicated source for 967. So if you look at that and 967, you'll see that they're very similar. Okay, inspection. Sorry, I'm running a bit over time. Visual inspection of all the accessible welds is pretty standard, and really, if you've got a decent QA system, it should be documented somewhere. If you're talking about welding of tube or pipe, then the exterior is a pretty poor guide unless you really trust the operators. And probably you should have some agreed system for saying, okay, we'll cut open every 10th weld or something and check it. And if it's bad, then you pay for it. And if it's good, then we pay for it. etc. Codes and standards recommend the various percentage of NDT. And if you're using a borescope to look at something, then remember, you are looking at a very short distance away, and you're looking at it at ×3, ×5 time of magnification. And so you see something that looks absolutely terrible, and then if it's cut open, you say, well, where's the defect? Because really, truly, borescopes give you the best possible image, but the worst possible impression. What about blast cleaning? Yeah, you might need to repassivate because it'll be too rough. And you also have to worry about whether you've trapped anything into the surface. We talked about that a bit before. Different colours show that fragments are embedded. And what can the various media remove? Well, anything that's hard enough, garnet, silicon carbide, it'll basically roughen the surface. You might get the chromium depleted layer, well, you will get the chromium depleted layer taken away, provided you make sure that you abrade it right next to the weld a bit longer. But if you're doing it with glass, then really you're not going to take much metal off at all. So is it clean? Well, dip it in, see if the water films up or whether it runs uniformly. That's a grease test. Atomizer test, it's about 100 times more sensitive. Solvent ring, it's an absolute pain to use. And yeah, you need to be good at it. Potential corrosion sites, if you do a wet and dry test, you'll get gross indications. Talked about that already. And the chemical spot tests, yep, like that. So what do you do about maintenance cleaning? Well, I'm sorry, this is a Stainless Steel Association thing. There are lots of others, but that one's freely available. So have a look if you're interested. If you've got steel, carbon steel brushes or scrapers, I love the story of some people in a food factory who said, oh yes, we're always careful. We always use the same brush for brushing our stainless steel. And when we said, oh, can we have a look? And we looked at it and we said, but hang on a minute, this is a carbon steel brush. And I said, oh yes, well, it's the only one we use for our stainless steel. At which point everybody laughed. No, I don't think. Hydrochloric acid will obviously damage. A lot of proprietary cleaners have chloride activated detergents, or they have bleach, or they've got hard and large abrasives. So you get Ajax scourer, and that really will tear the hell out of the surface. And post-cleaning rinse processes. The AMS 2700 in a lot of places suggest 200 ppm solids in it and thoroughly dry the surface. Otherwise you get water stains. And final slide, I think. Routine frequency of manual cleaning. It's going to depend on the environment. Rainwashing outside. The rule of thumb that we've used and lots of people have used is that if you're talking about a piece of stainless steel and you're comparing it to a window that's local to it, this is exterior, and the windows need washing because you can't see through them, then you should wash your stainless steel. By the way, you should also wash your paint surface on the outside because dirt and rubbish on the surface of paint does tend to damage it. And there's a couple of guides, comes out of Japanese standard. And if you're looking for interesting things, then that's the Euro-Inox publication, 16001, Pickling and Passivation. That's available from, look up Euro-Inox, Pickling and Passivation. And there's also the Nickel Institute and IMOA publication, which deals with practical guidelines for fabrication of austenitic stainless steels. There's also one on practical guidelines for the fabrication of duplex stainless steels. And thank you. That's it.
Thank you very much, Graham. If you all have any question concerning this presentation or about any nickel-related topic, kindly send us your question via our webpage. Once you enter www.nickelinstitute.org, you will immediately see the yellow banner Technical Help. Click on it, register, it's free of charge, and fill in your question. One of our experts will come back to you within 24 to 48 hours latest. Thank you all for attending this webinar. We are looking forward to have you on one of our next webinars again. Goodbye.